I will announce our today's speaker. This is Professor Boris Kruglikov, and as you see, he will tell us about dispersionless integrability, whatever it means, in dimension 5. Where I think you can begin.
Thank you very much. It's a pleasure to talk on Moscow Seminar at Независимый. So let me just start slowly. Let's join work with Umit Mahmali. Well, the archive references above. So I'll choose, well, nonlinear differential operator of order L. And for entire today discussion, I'd like to restrict to just scalar operator. So one, but it extends actually to more general settings. So two systems, but I will talk about scalar PDEs. So differential operator, PDE given as its locus, give us equation submanifold. And it's of course more convenient to work on infinite prolongation, which will denote infinity and defined by was composing the operator F with C differential operators. Okay, and then we need symbol. So I recall some important notions. So U will be dependent function. And if we do this combination, then we get linearization operator. But if you restrict to top multi-index alpha, then it's symbol of this. And it's important, of course, everything is just pulled back to infinite jets, that it's polynomial of the homogeneous polynomial of degree L on tangent bundle. So U will be usually denoted independent function, but for majority of cases, I will just restrict it to equations. Will be solution of E. And mu will be just base, but lifted to J infinity. And if U is solution, it will live in J infinity. So in the case of second order operators, so we will have the following story. But as I said, they may be systems indeed. This symbol is pure second order operator. And it's convenient also to write it through matrix. Indices should be actually upper here. So I write depend on U, but in fact it is, of course, depends on jet on U. So the difference between these two formulas is in one case that's ordered ij, in the other case it is actually entire summation. So diagonal sigmas are the same as this derivatives of f, and for others we have to split divide by 2. Okay, and given this, we can write characteristic variety. And it's just given by complete contraction of the symbol. This a covector. Well, that's a quadratic form. So in components, it means this. So P is covector here, right? So what we obtain here lives in cotangent bundle of our manifold, and well, U will be always be ground solution. So it's actually cone, right? It's quadratic cone, and in particular, well, this gives possibility to projectivize it. So convenient to have projective characteristic variety. Okay, and if the symbol well equivalent to characteristic variety is non-degenerate, which means that if you take determinant of the matrix of this bilinear form symbol, we get non-zero on generic solution, then we can invert this matrix. Okay, let me introduce notation. Gij with lower indices, and this will be matrix inverse to matrix sigma. So then we can form two tensor. I use local coordinates from base lift up to actually this solution mu. So this is a metric. And then the conformal structure on mu depends only on equation. Indeed, if we change defining function for equation f, it's scaled by something, and then sigma scaled by the same thing, and then g scaled by inverse of the thing. So actually, this g defined up to factor we get conformal structure. So this gadget was introduced in the work of Jennifer Apontov and myself. And it's important for geometric approach to integrability of dispersionless type. Okay, so let's look at example. Okay, so here defining function is this. So we compute the symbol. Then we form the matrix. If we take txy order variables, and that's dt dx, you see split it like 1/2 and 1/2. And then we have zeros around, -1 here, and the only non-constant coefficient will be for dx. And then we invert it. Okay, and then we basically get our metric. Well, conformal representative of it. And also it's a zero cone. Projectivize it gives us characteristic variety. And of course, non-degenerate characteristic cone uniquely restores the conformal structure. Okay. So now let me give the just general definition. So dispersionless Lax pair order K is a P1 fiber bundle. And rank to distribution. So I basically work here in real category. So P1 is RP1, so it's just circle bundle, but everything can be complexified right away. And sometimes it's actually convenient to I'll discuss later to to partially real, partially complex. The three conditions. So for every point of this total space, which is called correspondence space, this plane of the distribution depends only on case jet of the section. So it's locality condition, the first thing. So second is that this distribution, okay, let me write it in kind of local form. So M is kind of vector field on the base, and then we lift it to fiber. Y is coordinate in fiber in P1. So this two distribution is transversal to the fiber. And fiber coordinate is del lambda. Okay, so in fact, this X and Y also depends on lambda, as they're not just vector fields on the base. And finally, Frobenius integrability for this distribution. Well, probably I have to write sections of pi hat here. Modular equation. So non-triviality of flux pairs. A flux pair means actually the last equation essentially uses E. So there's possibility to change pi hat on shell on equation. But whatever change we do, so we cannot eliminate equation from this story. Okay, and so we also consider to plane congruence. Which is just projection of this distribution. Well, maybe proper from algebraic viewpoint is good to call it actually pencil, but in twistorial community, maybe congruence is more adapted. So in other words, that's those vector fields X and Y from the definition and a span of them. And so here X hat is just point on the base in lambda. So lambda is spectral parameter. Okay, so yeah, the distribution pi hat is not projectable, but we still project it, and therefore we get one parametric family of planes on the base, and they are parameterized by this lambda. Okay, and then we get twistorial picture. So n is just dimension of the base plus one dimension. That's our P1 bundle from the definition of dispersionless flux pair. But then here on M hat we have distribution, which on solution is integrable. That's rank 2 distribution by hat. So when we quotient locally by it, maybe globally, but usually it's just local quotient, then we get what's called Twistor space. So at minus 2 dimensions. Okay, so let me just mark the names. The Twistor space, that's solution manifold, and that's correspondence space. Okay, so maybe I'll later return to it if time permits. I discuss different twistorial approaches. Okay, and now I would like to formulate one result from my work with David Calderbank. So we proved with David that dispersionless pair must be characteristic. That's in fact very general statement. We don't need quadratic characteristic variety here. Can be absolutely arbitrary system, but we want determined. So it should be determined system. So what means characteristic? That means that for any solution, for any point on this correspondence space, and for any covector which annihilate this plane from congruence, so plane leaves in tangent space, also annihilator leaves in cotangent space. We have that symbol vanishes on this covector. In other words, that covector is in characteristic variety.
I'm sorry. What in your geometrical definition is responsible for dispersionlessness?
Second order. So
second
basic
order. Just second. Okay, thank you.
Yeah, and kind of the geometry is sketched by characteristic variety. Yes. So that's more or less what I need. The examples are dispersionless, but I don't know actually what means be dispersionless, but let's accept this as definition. Okay, so let's just understand the theory. So this means this is plane phi hat is coisotropic. For this conformal structure, and it's quite elementary that such planes exist only starting from half dimension. Therefore, n should be between 2 and 4. So in tangent space, they are. Okay, so let's consider possibilities. For n equal to 2, no restrictions. Well, just one plane, tangent plane, two-dimensional, so it's, of course, coisotropic. For n equal to 3, we have three-dimensional space with Lorentzian metric. Therefore, we have Lorentzian cone, and the condition is that plane is tangent to it. So it's clear that what we get, the space of such planes, is just cone itself. And finally, for n equal to 4, we talk about planes of half dimension, which should be totally null. And there are two such. So there are two rational, disjoint rational curves. So if you write the equation for four-dimensional, let's take it to be of neutral signature to 2 in 4 dimensions. And if you write equation for total null planes with arbitrary parameters, it's completely resolvable. And that's in rational expressions. So that means actually that it's rational curves. But there's two components. So both are phi1, and to distinguish them, and yeah, there's one parameter there. To distinguish them, one is called alpha, the other is called beta. So sometimes they called alpha planes and beta planes, sometimes they called self-dual and anti-self-dual planes. Okay. So now let me formulate corollary of this. For n greater than 4, PDEs with non-degenerate quadratic characteristic variety are not integrable via dispersional flux pairs. Okay, maybe a short example. So let F0 be an integrable non-degenerate differential operator in 3D or 4D. An extension of this kind. I just add Laplacian in new variables. So here I have 0 independent variables are like x1, x2, x3, or maybe x1, x2, x4, and I add Laplacian in the other variables we would like to extend. Maybe sign indefinite Laplacian, but flat. Well, even flat case, then the thing is not integrable. Well, we have to exclude linear cases, of course. And particular example of the situation is DKP to Khokhlov-Zabolotskaya. So DKP is three-dimensional. If you just add double derivative in the fourth variable, not integrable, or in higher dimensions. Yes, so there were some attempts, but it follows just from corollary. Okay, so let me, before I go to actually 5 dimensions, let me recall what happens in dimensions 3 and 4. So, and what I would like to recall, integrable background geometry. Namely, restrictions on this conformal structure which appears well before. So that what constraints on those structure should appear. So in 3D, it is Einstein-Wall restriction. So Einstein-Wall structure, let me recall this, is a triple. Normative manifold. There's 3 structures: conformal structure, then one form, and connection. So conformal structure, and then there's one form or covector, called also Weyl potential, and then there's torsion stress connection. So this triple is restricted by 2 equations. The first equation tells that the connection preserves the conformal structure. So if I just write nabla of square bracket g, I have to write 0. Well, I have to write it's equal to square bracket g. But if I choose representative metric, then actually I should get something which is proportional to g. Coefficient of proportionality is this one form omega. Okay, and this relation actually allows us to have 2 ingredients out of 3. So if you have G and D, we find omega. If you have G and omega, we uniquely find D, by the condition that D is symmetric, torsionless. Okay, that's just Weyl structure. And then we compute Ricci, we'll compute Riemann tensor of connections, and we compute this Ricci part. Ricci part contains, in this case, symmetric and skew symmetric parts. Skew symmetric is not very much interesting. It's just differential of omega, but symmetric is interesting, and we claim it should be proportional to G. So lambda is coefficient of proportionality. If connection is metric, Levi-Civita, it should be constant. But for general context of conformal connection at maybe function. Okay, so let me take example. So Einstein-Weil equation from DKP. So we already started with this. So let me continue. Okay, I write the equation again. Correspondence space was the base is three-dimensional correspondence spaces. 4-dimensional, there's base coordinate and the spectral parameter. Symmetric, that's what we obtained before. And so, and that's, well, actually, it's conformal structure given by this representative. The only thing which actually lacking for Weil structure is covector, and here it is. Okay. In this case, these data give us this distribution, which is actually Lux pair. Okay, so integrability here is encoded through Einstein-Weil. And in 4D, the integrable background geometry is related to self-duality. So the main invariant of conformal structure is Weil tensor. So we assume that conformal structure is neutral signature. And in this case, Weil tensor splits into self-dual plus part plus and the anti-self-dual part minus. Hodge star act by plus on first part and by minus on the second part. And conformal structure is called self-dual or anti-self-dual if W minus vanishes or W plus vanishes. In other words, if W equal to W plus or W equal to W minus. Okay, and let's have example here. So the second Polymansky equation has self-dual conformal structure on solutions. So the metric here, well, representative for conformal structure is this. And the corresponding alpha family of planes, which is going to be dispersionless pair, is the following. Okay, there's a bit difference here between this Lux pair here in 3D and this Lux pair here. So, namely, the first one you see, it contains derivations with respect to spectral parameter, and therefore it's actually linear non-degenerate, equivalently called not weakly nonlinear. And here, these Polymansky equations actually does contain d by d lambda, so it is weakly nonlinear. So we will see possibilities for both, and in general, of course, it is not weakly nonlinear, so it is linearly non-degenerate. And indeed, the master equation for this situation contains d by d lambda terms. Okay, okay, now I would like to discuss higher dimensional situation. So for integrable, it is with quadratic characteristic variety. Yeah, of course, not all PDs are such thing. For example, like Oleg Morozov was considering last time the PD for which characteristic variety is actually reducible of degree 3, right? So here I consider specific situation, but that corresponds to wide class of dispersionless equations. So the maximal rank of the symbol is 4. That's the corollary above. Whence the distribution Now I would like to introduce one of the important features of the high-dimensional situation. So I take this symbol, which is 2 by vector, and I construct it with all symmetric by vector, right? And I construct it with all possible covectors. So then one vector index gone, it was 2 indices down, one just remains. So we get a linear subspace of vectors. In other words, it's vector distribution. So this distribution has rank at most 4. So in general, this distribution is non-holonomic. There's no reason why Frobenius condition should hold for it. And indeed, examples show this. For generic solution of our equation. The symmetric bivector sigma f on this distribution is non-degenerate. Therefore, we can compute its inverse as before we did on the entire tangent space, but now we do it only on distribution. Defines in canonical way subconformal structure. So there are sub-Riemannian structures just defined on distributions. Of course, signature can vary, so it will be sub-pseudo-Riemannian structures, and then if things defined up to scale, it's going to be subconformal structure. Non-holonomic distributions can have various symbols. Oh, okay, weak derived flux, first of all. And then symbols given by brackets of vectors. So there's a whole variety of things in general, but most of them are incompatible with requirements from integrable background geometry. So in what follows, let us restrict to just 5-dimensional situation And then the distribution has generic behavior, which is contact. So we have rank for distributions 5D. That's what we would like to study. So we have the following data. So here I just do geometry, so I will omit all reference to equations and solutions. So we have 5-dimensional contact manifold. So we have then conformal metric on the distribution. And for simplicity, let me assume it's of neutral signature. Then there's this contact distribution, right? As contact form, I can differentiate it, and I get two form, which is defined up to factor. So I get this thing. Which is conformal symplectic form. And then I have two non-degenerate forms, one symmetric, one skew symmetric on distribution, both non-degenerate, so I can divide by y by the other. In other words, I can take this symplectic form omega and I can raise one index. Right? So I get endomorphism. And both G and omega are just conformal defined up to factor, so but J can normalize by choosing combination of those factors. I just will require that operator norm is 1. Okay, now definition So subconformal structure or namely all those ingredients is compatible, or these ingredients are compatible. If alpha, same as self-dual family of null planes, so now we have 4-dimensional delta, and we have metric of neutral signature on it. So we can have two families, alpha and beta. I choose one, so it's actually determined by orientation. Well, there's two choices, and the swap of the choices changes this alpha and beta families. So I would like that this family consists of G null, well, that's definition of alpha, but here's requirement, omega Lagrangian planes. So this collection is just one parametric family, so it's give us P1 as before. Well, okay, it's alpha family, let me put alpha. But beta family here will have no chance actually to contain the null G null omega Lagrangian planes. So it contains just finitely many of such, namely 2 or nothing. Okay, so how is this compatibility condition right through these three things? Okay, two of them, G. So here's the formula. It actually says that J is orthogonal endomorphism with respect to G. Also, it implies that J square is proportional to identity. Coefficient of proportionality is 1 or minus 1. And trace of J is 0. So the number of plus 1 eigenvalues is 2, and the number of minus 1 eigenvalues is also 2. Okay, so if delta is equal to plus 1, then we have that G null, omega, Lagrangian planes are either eigenspaces of J, let's call them L plus minus, the eigenspaces of J corresponding to eigenvalues plus minus 1. And that's those two, right? L plus 1 and L minus, that's discrete. And then we have family. So family is obtained as follows. It's generated by two lines. So one line in L plus, one line in L minus. And they are orthogonal. Okay, so these are now planes. Therefore, the second plane is dual. And choosing L minus, we uniquely find L plus. And amount of L minus is just projectivization of L capital minus, so it's P1. Okay. And if delta equal to minus 1, then G null omega Lagrangian planes form one parameter family. Phi of J invariant null planes. Okay, so that's two geometries. So actually, yeah. So we both are realized, and both are integrable in this sense, and they have names. So some combinable subconformal geometry with delta equal to plus 1 is a Lagrangian contact geometry. So contact plane is direct sum of these two Lagrangian planes. And it is so-called parabolic geometry of type SL for R mod P13. Okay, I'll briefly tell what it is. So if you take Lie algebra of SL4, So then that's grading here. So the zero parts here. So you see 6 zeros, but there's trace condition, so it's actually 5-dimensional. And plus 1 part is 4-dimensional, and plus 2 part is 1-dimensional. So altogether, this P13, its non-negative part, it is 10-dimensional. And if we quotient is solve over P13, then we get a model, namely 5-dimensional contact manifold, and contact structure corresponds to, that's L minus 2-dimensional, and that's L plus 2-dimensional. There's a direct sum. It's easy to see that they actually Lagrangian here, but that's a model, right? So in general, it can be curved. So, and as corollary of the general story, so this Cartan geometry has harmonic curvature. Okay. So it contains 3 parts. So sometimes the big curvature decomposes into pieces like geometric, scalar, Ricci, traceless, and while. So here appear also some while, but the other parts actually are kind of torsions. So let me write approximately where they live. So these are tensors of the following kind. Okay, so torsions are very simple. So we have the distribution L minus, so it's Lagrangian. Therefore, if you take brackets of it with itself, it cannot leave contact plane, but it definitely need not be integrable. So the first derived of rank 2 distribution may be rank 3, and therefore it will intersect L plus. That's tensorial. So if you project this brackets to L plus, that's tensorial piece. That's precisely tau plus, and similar with tau minus. So we see this 1-dimensional piece, tensor, and this 2-dimensional. So both tau plus and tau minus have just 2 components. Okay, so the curvature part is more complicated. So there are some densities bundles involved in here. Okay, so this wedge 2 of L minus and L plus, there's just 1-dimensional densities. Annihilator of delta plus, it's also density is 1-dimensional, but this fourth power of L minus, it's 5-dimensional. And that's another 5-dimensional here. So one might think that actually the story is like with wild tensor and 4D, which has wild tensor has 2 pieces, both with 5 components. But here L minus and L plus, they're dual. And in fact, this duality well, just duplicate those components. So this has just 5 components. Okay, so maybe let me not discuss in details the case -1. So let me just mention that it's almost CR hypersurface type geometry. So in this case, delta will be not split, but actually complex, and kappa H will have one torsion with 4 components. So only 2 reducible pieces here. Okay. So then to formulate the why we all need this. Okay, so here is the we approach the main statement. So if 2 3D plus 4D, and that's due to joint works with Jennifer Akontov and David Calderblanc, then there's kind of equivalences. Integrability by hydrodynamic reduction. And then existence of dispersionless flux pair. And then integral background geometry on solutions. Okay. So these things turns out to be equivalent. The bottom error was proved in most generality. The other two for certain classes. And if you talk about 5D, then the result is the following. The integrability of equation with dispersionless flux pair is equivalent to the zero curvature condition. So note this is tensor W. This is curvature. Similar to W plus and to W minus in 4-dimensional situation is quartic. Namely, its force power on the plane or in inhomogeneous parameter we can write it as just degree for polynomial. And this parameter is precisely the spectral parameter. Okay, so there's 5 equations. These are second order expressions. But there's also gauge group behind. So if we eliminate, similar to what we did with Marcin Dunarsky and work with Zhenya, then it's possible to write master equation. So, and basically that's just eliminating gauge makes one of those coefficients, for example, W4 equal to 0. Then there's nice canonical form, and will be 4 PDEs of second order on 4 known functions of 5 variables. Therefore, yeah, this is called everything. So maybe let me do the last example of all the situation. And okay, so let me give the last example. Okay, so 5-dimensional version of Plebanski equation. So here is the operator. Well, I will call independent variables x1 to x5. So that's rather like a version of first Plebanski equation. Then I compute linearization. Okay, and that's in the following notation. V1 is D1, D2 is D2, V3 is D5 minus U2 3D4 plus U2 4D3, and V4 is U1 3D4 minus U1 4D3. Yes, and in this case, that's the same as symbol because there's all of them higher order. So the distribution of equation will be just spanned by this V1, V2, V3, and V4. So that's an angulator of one form omega, which turns out to be contact form on generic solution. And then G is sigma f minus 1 is omega 1 dot omega 3 plus omega 2 dot omega 4, where these forms, okay, that's 0, are just dual to the above basis. That's co-frame dual to the above frame. Okay, and so here alpha planes are given by the condition omega1 is equal to minus lambda omega4, and omega2 is equal to lambda omega3 in terms of co-basis, or in terms of co-frame, in terms of frame, we can write it as spanned by this. Okay, so the dispersionless Lex pair is brittle from those. And we see spectral parameters enters, but not in form of differentiation. That's again linearly degenerate situation here. Okay, so that's kind of an example, and yeah, there are more examples, but I probably have to stop here. Thanks for your attention.
Thanks a lot. It was very interesting. Was questions, remarks? And reference to your preprinting is in
Yes,
your abstract, yes?
yes, it is here. Yeah, it's the same title. Yes.
Okay, thanks a lot. So no question, no remark?
Maybe one question, Iosif.
Женя, какое странное у вас имя. Yes, of course.
Sorry?
Yeah, I couldn't guess who is M-A-E. Yeah. Oh, now, yes. Now,
MA, the mathematics,
yeah.
and then my initials.
Yes. Now I understand. Okay, Женя, you're welcome.
Right, Bora, thank you very much. So this last example, it belongs to which type? First type or second type?
To the first type.
Huh?
To the first type.
First
Delta
type.
equal to +1. Yes.
Do you have examples of the second type as well? Similar PDEs.
Not with name.
All right.
No questions. Okay, Boris, thanks a lot. It was very interesting, and I hope it will be not your last talk here. So
Okay.
we skip the next Wednesday, and I do hope that we meet in 2 weeks. Have a nice time, and goodbye, and thank you for joining us.
Bye-bye.
Bye.